Hey guys, this is Mrs. Harbin, and this is Algebra 2, and today we're looking at section 3.4, Graphing Systems of Inequalities. So we just solved systems through graphing, and those were all linear functions, and when we solved those systems, they had one point of intersection. But not everything is nice and neat and intersecting at just one point. Sometimes things intersect at multiple points. So that's what we're going to take a look at today when we graph inequalities. Our biblical integration for our unit is this. John 3:16 says, "For God so loved the world that he gave his one and only Son, that whoever believes in him shall not perish but have eternal life." And we've been talking about at the beginning of each lesson here, how Jesus is constant. We're told that, Jesus Christ is the same yesterday and today and tomorrow. There is no variable. He doesn't change. So we don't need to, a year from now or 3 years from now, sit down and go, man, I wonder what Jesus means in this day and age. Like, Jesus is the same. That's not what's changing. But we are going to deal with things that are variables. Prices are variables. Supply and demand is a variable. And so systems of inequalities and other systems can help us solve those problems, solve those variables, so that we can hopefully do what God has given us the task of doing, using our gifts and abilities to bring him glory. Our lesson objective for today is this. You, the student, will solve systems of linear inequalities by graphing and identify the vertices of the region containing solutions to a system. So take a look at this. This is a graph, a break-even analysis that shows us two different functions that have been graphed. And you can see to the right here, we've got profit, and to the left, we've got loss. And this region between the cost function and the total revenue function is this break-even analysis. And companies use it to represent their profit and their loss. This break-even point is where these two functions intersect, and that's where they want to be. Obviously, companies want to be more towards the profit side, not so much toward the loss side. We want their prices to be lower because we don't want to pay so much. We talked a little bit about that in class with that supply and demand. And so that break-even point is where the cost of making their product and then the cost of the fixed cost is break-even. So if it costs you $5 to make your product and you sell it for $5, then that's your break-even point. And so this flux between supply and demand really hinges around that break-even point. And companies can use this system of inequalities to kind of determine this point. So we're going to work through some examples together. Again, you're not learning anything new in this particular lesson. You've graphed inequalities before. You've solved systems before. The steps are the same, but now we're going to apply it to some real-world problems. But let's do some just with numbers. Okay, no problem solving, no variables that we have to determine, just practicing the steps. So we've got two inequalities here, and we are going to solve both of those inequalities and put them in slope-intercept form. Okay, instead of y equals mx plus b, we've got y is less than or equal to, or y is less than on the right-hand side here. Once we have both of these, we can go ahead and graph these inequalities. Just a reminder that when you have a less than or equal to sign, that equal to part is going to give us a solid line. And just a less than or greater sign, no equal to, is going to give us a dotted line. So let's graph the first inequality and graph the second inequality. So our first inequality looks like this. Solid line, and it says less than or equal to, so we're going to be underneath the line here. And our second line is y is less than negative 1/3 x, so here's our dotted line here, and again less than, so we're going to be underneath the line. And then you can see that there is a point of intersection, but instead of just one point of intersection, we actually have a whole region of intersection. This whole region is both red and blue. It satisfies both inequalities. We are going to choose a point to test, any point in the shaded region. When we plug that back in, it should make both inequalities true. If we choose, for example, 0, -3, and we plug that back in, we get that this is less than or equal to 4, and over here less than -6. If you plug those in, you'll find out that -3 is less than or equal to 4. That's true over here. And over here, we would get -9 is less than -6. That is also true. So because both of those statements are true, then this is the correct shaded region. That is our point of intersection. Now, we can't list that as one specific point like we could do with linear functions or linear equations earlier. We're just looking at our region. This region is our point of intersection. Okay, let's try another one. This is the exact same one, I think. It looks exactly the same. I'm not sure why it's on here twice, but there you go. You get to see it twice. All right, the inequalities being graphed are not limited to linear inequalities. So let's take a look at this one. We have y is less than or equal to the absolute value of x plus 2, and y is greater than or equal to the absolute value of x minus 1. Remember, absolute value functions are going to be in the shape of a v, so we should end up with two v's here. Let's graph our first inequality. Got a solid line there, and graph our second absolute value function here, inequality. There is our second one, and we've shaded the region. It says y is less than, so we shaded below. And for the second one, y is greater than or equal to, so we shaded that blue above. And here, in this kind of slightly purple area, you can see our point of intersection. We can choose a point to test, like 1, 1, and it should satisfy both of these inequalities, which it does. There will be times when you want to know the vertices of a region where inequalities overlap. So let's take a look. This is example 4 in your book, but we're going to graph the system and find the vertices of the region representing the solution. So this time we have 3 inequalities. So we are going to graph all 3 of these inequalities. We've got our green one right here. We put it in y equals mx plus b form. These should not say equal necessarily, but there they are. X plus y equals 2 and x minus 4y equals 12. Okay, they mixed up the colors a little bit here. That should be this one, and the one that's green over here is actually red over here. Again, pay attention to these signs here. They're written with equal signs over there. They should not be. They should still be greater than, less than, all of that. Just a quick reminder here, you'll notice that the sign did switch because we divided by -4, and when you divide by negative, you've got to flip that sign. So graph the 3 inequalities, and if we were to shade those, we would see this point of intersection would be right here in the middle. And it may be kind of difficult to see once you get 3 different regions going on, so you may want to do more than just shade. You may want to do a pattern above or a pattern below. Okay, let's take a look at these. We've got y is greater than or equal to 1/4 x minus 3. That's this right here, okay, and it's greater than or equal to, so we're going to shade above this way. We've got y is less than negative x plus 2. Okay, that's this one right here because it's less than. We're going to the left, so I'm going to just do lines here. All right, and then our last one, y is greater than or equal to, it's going to end up being y is less than or equal to, because we've got that negative y there, 2x plus 4. Okay, and that's this one. Y is less than, so we're going under. And you can see here where I've drawn my lines, the area that has the all three patterns, all 3 lines is right here in the middle. That one is difficult to see. Okay, if we want to know then the vertices for that region, we would identify the 3 points of that triangle. And there we have -4, -4. 4, -2, and -2/3, and 8/3. Okay, you can use this graphing method, or you can use it algebraically. If you wanted to use substitution or elimination, you can solve that way as well. All right, today we solved systems of linear inequalities by graphing, and we identified the vertices of the region containing solutions to a system. Again, this is nothing new, no new steps. We're just taking the steps that we already know in solving systems, and we're putting them into word problems, putting them into practice. If you have any questions, make sure you ask me next class.